yesterday with regards to compound interest, right? We said that compound interest grows exponentially. That's not the only thing in this life that grows exponentially. Okay, so we got 3 examples today that we're going to look at here to begin class of where exponential growth or exponential decay are being used. Okay, so let's start by looking right here at Rebecca. Rebecca is training for a marathon. Is that up y'all's alley? Any of you guys are runners, aren't you? I got a couple of runners. Joe, you run a little bit? Yeah. So I have run a half marathon. I've never run a whole marathon, but the whole thing, man, it comes down to training, right? It comes down to putting in the effort, putting in the work way in advance to the actual event. So Rebecca is doing just that. So she's currently going about 5 miles on her long run. You know, each week you have a long run, usually on like a Saturday or something. And so she's going to plan out that each week she's going to bump up that long run by 10%. Okay, so like her next week's long run, right? 10% of 5 would be 0.5. So her next week's long run will be 5.5 miles. And she's not going to increase it linearly. She's not going to continue to add a half mile every week. She's going to grow exponentially. So the next week, that 10% of 5.5 would be 0.55 miles that she would tack on. So she's going to start adding more and more and more each week. That's the idea of exponential growth. So what we want to do is we want to determine, based on this, will she be able to hit a 20-mile training run within 15 weeks? Okay, so let's talk about our parameters as we did the other day. Our formula, typically speaking, is A equals P 1 plus R over N to the NT. Okay. Now, in this case, P is what she starts with. In the financial application, that's our principal investment. How much is she starting with here in this little example, Ben? Very good. So our P value in this case would be 5. Okay. We got 1 plus. Now her rate is 10%. Mossy, how do I want to express that in calculation? How do I always express a percentage when we're running the numbers? Do I just write 10? No. What do you want to write? Okay, so what would 10% be as far as a fraction goes? Good. 10 over 100 is the same thing as 1 over 10. And then if I convert that to a decimal, it would be 0.1. And that's what we want to use. Make a note. We want to use a decimal. All right. Now, N is the number of times per unit or per unit of time that she is going to be upping her mileage. So if it says like each week she's going to be upping it 10% and she's going to recalculate every day, that would be different, right? That would be where N is 7. But here it says we've got a weekly increase rate of 10%, and she's just doing that computation once a week. So N is 1. This will be like the bank that says we'll pay you a yearly interest rate of, you know, whatever. I think yesterday's example was 12%, and we'll only compute that annually. In other words, we'll just do it once a year. So that N value is 1. So here we've got 1, and then what's the duration of this experiment? What do you think, Drew? 15. That's going to be my T value, so 15. And we want to see, is this going to end up equaling that 20-mile mark that she's trying to hit? Okay, so it's a simple plug and chug. The hard part about this word problem is realizing that the same formula can apply outside of the context of finances. So we get a calculator out, which I'll get mine out for us. When you're doing exponential growth word problems, it is very important to have a calculator to run the numbers for you, because the numbers can get real big real quick in most cases. So let's do 5 times 1 plus 0.1 over 1 raised to the power of 15. We hit enter and we get 20.886. So Luke, what do you think? Has she hit her mark or not? She certainly has. So in this case, we would say, hey, she's got enough hay in the barn. She'll be all right. She's going to make it. A lot of times, to go back to the idea of the finance application, a lot of times it's like saying, well, hey, I'm saving for college, or I'm saving for my daughter's wedding, or I'm saving for retirement. And the question is, will I have enough? You know, and so we can do a little bit of planning ahead. Any questions on example 5? All right, then let's look at example 6. This one's a little bit strange because we're going to be decreasing. This isn't exponential growth, it is exponential decay. Very good. So this is going to be one little twist that we introduce on this problem. And I want to ask if you guys remember, anybody at home, I'll throw this your way. Does anybody remember what we said the stipulations were for decay as opposed to growth? How does one determine whether or not it's decay based on the formula? Anybody at home remember that? Tiago, what do you think, buddy?
I think it was if one of the numbers is less than 1.
Yeah, very good. Our base must be between 0 and 1 for it to be decay. If the base is going to be more than 1, it's going to be growth. Look at this last example. And fellas, right here, you tell me in the parentheses, is this more than 1? Of course it is. That's 1 plus something. So we knew that last example was going to be growth. How do you think I could make my base less than 1, James? Very good, very good. 1 minus something. So again, here's my formula. A equals P 1 minus R over N raised to the NT. That's going to be our formula for exponential decay, right? Now it says we're given a rate of 2%, so I know to plug that in is 0.2, right? Don't you dare say yes. 0 to, good. Me getting a little tricky on this beautiful Tuesday morning. Let's see here. They're increasing, or excuse me, they're decreasing. They measure it once a year. All right, so how much does it start off with? The population is currently 152,000. And we're going to subtract 1 times 5. How many children were there 5 years ago? Actually, you know what? I did this in yesterday's class as well. I'm going to highlight something, and you guys tell me what you think. How do I've misinterpreted the problem. I've messed something up. How do I fix this idea of 5 years ago? What do you think? If I put my 152,000 where P goes, Turner, have you taken care of business yet? Just waiting on him? Okay, cool. If I put my 152,000 where P goes, and then I run the numbers, imagine that's where P is 152,000 and it is decreasing. That's not what the case is. The case is where today is 152,000, and then 5 years ago it was what? It was higher than that. So we want to say 5 years ago we started up here, and then we decreased down to 152,000. So what could I do then? How could I set that up? If my unknown is what I started with, and now I've got 5 years later, 5 years in the process, now I've got 152,000. Where can I plug the 152,000 in? James? Let's plug it in for A. Like I said, I was hustling through this yesterday in my freshman class, and I made that same careless mistake. What we're doing is we're going to plug in 152,000 in for A, and we're going to say, let's solve for P. Now, logically think about that. Let's say I get P is like 100, I don't know, like 170. Let's just make up a round number. 170,000. That's like, and then you put yourself in a time machine, you go back 5 years, you say, okay, guys, we've got a population, school-age population for children of 170,000. And then we play out the decay for 5 years, and it takes it down to 152,000. That makes sense, because that person 5 years ago would say, in 5 years, how many people are there going to be? He's asking, what is A? In 5 years, what is A? And then we know from the problem here that A is 152,000. So we want to get P by itself in this case. Right now, P is being multiplied, isn't it? Okay. So Lewis, how do I undo multiplication? What's the inverse op of multiply?
Dividing.
Yeah, so if I want to get p by itself, I'm going to divide both sides by this parentheses. 1 minus 0.02 over 1 raised to 1 times 5. And then that cancels out, and we got p by itself. Now I'm actually going to go ahead and run the numbers on my calculator. All right, so 152,000 divided by parentheses 1 minus 0.02. That's just 0.98, isn't it? I'm just going to go ahead and write 0.98. 0.98 raised to the 5th power, right? And run the numbers, and I get 168,156, thereabouts. So 168,156. Thereabouts, okay? So that's approximately how many children there were 5 years ago. And it's decreased over the last 5 years down to the point at which it's 152,000. Okay? That one's a little weird, right? James identified for us the fact that since it was decay, we needed to subtract. And then we also had that curveball of, all right, we're going in, I've highlighted in green, we're going in the past. So we were looking for P, the principal, the initial population, and we had A, the amount after the 5-year period was over, okay? So example 6 make pretty good sense? Questions that you guys might have? All right, let's look at this last example here. Oops. Now it says the value of a particular piece of land worth 40,000 bucks is increasing at a rate of 1.5% per year. You guys know that land typically increases in value. What's something that decreases in value usually? Yeah, automobiles. As soon as you drive that brand new fancy pickup truck off a lot, it now has depreciated in value. Land, on the other hand, you buy it and you sit on it or you live on it or whatever, and then it typically appreciates in value. This one is increasing at 1.5%. Now, assuming that rate continues, it says how long? So what am I looking to solve for right here, Charlie? If it says how long, that's telling me my unknown is what? Very good. I'm going to end up solving for t. Now, that's an interesting proposition. It's a good segue into our main lesson for today, 10.3, because where does t show up in my formula? It's an exponent. And up to this point, we haven't perfected a major way to solve for an exponent. We haven't perfected a major way to solve for an exponent yet. That's where logarithms are going to come in handy. But let's set up our formula here. We got A equals P1 plus R over N to the NT. Okay. Let's see what we know. What does P stand for here in this case? What should I plug in? How much is the land initially worth? 40,000. Good. 1 plus. Now my rate is 1.5%. Drew, turn that into a decimal, please. 0.15. 0.15 will be 15%. Let's take it over one more to the left. 0.015. By the way, this brings up an interesting skill from pre-algebra, being able to convert percents into decimals. Remember, fellas, the trick is you move the decimal 2 spots to the left to go from a percent to a decimal. Or as Mossy accurately put it, we divide by, Mossy, we divide by, oh, bro, percent. You said a minute ago when I was asking you about a percentage, you said divide by 100. That's what percent means, right? We divide by 100. So scooch that decimal over to the left 2, or just divide the number by 100. Either way, we got 0.015. That's our 1.5%. And then how many times does this land appreciate per year? Yeah, just once. That's a simple calculation. It's just an annual appreciation rate. And then let's see here. So we got 1 times t is just going to be t. Let's clean this up a little bit. I haven't been cleaning this up much. But we're going to go 1.015 raised to the t. And it says, how much does he want to get for it? In other words, what does my a need to be? 50,000. So 50,000 right there. Okay. Now, here's my recommendation. I'm going to divide both sides by 40,000. Right? Divide both sides by 40,000 because not only am I trying to get t by itself, but I also notice there's 4 zeros, there's 4 zeros. I can cancel that out. I can get 5/4, or 1.25 equals 1.015 to the t. Okay? Now, at this point, I said we don't have a great way to solve this equation. So what we could do is we could just run the numbers and kind of brute force it, right? So like I could say 1.015 to the, and then let me think of like how many years is it going to take? Maybe it's going to take 10 years. Maybe I'll raise it to the 10th power. Is that 1.25? No, I need what? More time. So maybe I'll do 20 years. Is that 1.25? It's more than 1.25. So I don't need 20 years, and then I can kind of narrow it down from there, like guess and check. In other words, you guys use guess and check, right? So we can go and maybe split the difference. So 1.015. I'm gonna guess 16. Ooh, I'm getting close. What do you think? Maybe 15? 1.25. Boom, got it. 15 years. So I got that by guess and check pretty quick, right? But let's talk about a legitimate way of actually solving an equation that looks like this, okay? In your notes, I want you guys to write down that in order to solve an equation where the variable is in the exponent, you have to do one of two things. You got to do one of two things. Okay, so to solve an equation that looks like these three guys right down here, you need to do one of two things. You need to either make the base the same, okay? So make the base the same. That's your first option. Or your second option is, if you can't do that, consider using a logarithm. Now, logarithm is spelled L-O-G. That's how we abbreviate that word, by the way. A-R-I-T-H-M. Logarithm. Quentin. I'm about to show you with these three examples how we might consider making the base the same. All right. So like looking at number 4 right here. Okay. So 3 to the x equals 27. Now 27 I happen to know is a special number with regards to 3, right? 27 is what? Louder. 3 to the third. 3 cubed. So if I can rewrite, if I can rewrite 27 as 3 to the third, oh mama, now the bases are the same. And just visually speaking, what do you think x now equals? I got 3 to the x equals 3 to the third. What do you therefore think x is going to equal? Yeah, x is going to equal 3. Okay, so x equals 3. Let's do another one. I got 2 to the x equals 1/8. Now, 8 is a special number. 8 is what? Say it again, James. Not the cube root 2, the 2 cubed. 2 cubed. So 2 to the third power. However, it's in the denominator. How do I go about, Jake, do you have a microphone that works? Jake, how do I go about moving that 2 to the third up to the top? What's 1 over 2 to the third the same thing as?
2 to the negative third.
Very good. 2 to the negative third. Now, the base is the same. Now I got 2 to the x equals 2 to the negative 3. So what would y'all conclude about x? Yeah, it equals negative 3. The reason being is that we are making use of an old exponent rule from first semester that says a to the x equals a to the y if and only if x equals y. Write that old exponent rule down. We've talked about that before, but it's been a minute. Okay? And what that exponent rule says is, hey, if I can make the base the same, then my exponents must therefore also be the same. Like we just had 2 to the x equals 2 to the negative 3, therefore x equals negative 3. Right? How about number 6? Can you guys chew on that one? 5 to the what equals 1. Can I make the base the same? 1 is the same thing as 5 to the 0 power. And if 5 to the x equals 5 to the 0, we would conclude, therefore, that x equals 0. So my first technique for solving an equation where the exponent or the variable is in the exponent, my first technique is to say, ooh, man, could I make the base the same somehow? And if I can, let me think about doing it that way. All right. But that naturally begs the question, okay, well, what if I cannot make the base the same? Go back to our last example from 10.2, right? And you look down here at this equation, and you daggum tell me that those bases could be expressed as the same number. You're a better man than I. A 1.25 and 1.015, I've got no clue how to make them the same base, right? Earlier, we were dealing with easy numbers like 27 or 8 or 1. And those numbers we're readily able to work with. I don't know what the dump to do here as far as making the base the same. So what did we say consider doing now? Using what is called a logarithm. In your notes, write down, a logarithm is a tool by which we solve for an exponent. So I'll say that up here. A logarithm is a tool with which we can solve for an exponent. All right, a logarithm is a tool with which we can solve for an exponent. Because really, you guys have been learning the inverse ops. You know that add and subtract undo each other. What else? Multiply and divide undo each other. What else? Squaring and square rooting, cubing and cube rooting, raising to the fourth and taking the fourth root. In other words, powers and roots undo each other. Heck, that's the phrase it pays, isn't it? Power of root. Powers and roots undo each other. Those are all examples of when the variable is down on our normal level. Like x plus 5, well, duh, just subtract 5. But now we're learning how to handle equations where the variable is up top. The variable is raised up as a power. And we're going to use what's called a logarithm. All right? Check this screen out right here. Can I zoom out enough? Yeah, there we go. There's a lot up on this screen, so let's talk about it. All right, so first and foremost, you got to understand that a logarithm is an inverse operation to exponent, to the exponential function. And a logarithm has two parts. I know there might be circuitry overloading going up here, so let's just focus on this first little piece, just this first little piece, okay? So a logarithm is the inverse operation of an exponential function. We talked about that. It's how you solve for an exponent, okay? And let's look over here at this relationship. Can I zoom in right here? I'm gonna zoom in. All right, so like check this out. Every logarithm has two things. It has a base and it has an argument. Much like every radical has two things. A radical has the root or index that we've talked about before, right? And a radical has the radicand or the argument, more generally speaking, the argument of the root, right? So every square root or cube root or third root or fourth root has two distinguishing characteristics. It's got the kind of root that it is, and it's got the kind of argument that it has, or what we're taking the root of. That's our argument. Similarly, every logarithm has two things. Like, for example, here. This reads log base 10 of 7. Okay? You might jot that phrase down. I'm about to sneeze. Excuse me. So this reads log base 10 of 7. So not to ask a stupid question, but what's the base on that little example? 10. And what is the argument? In other words, what are we taking the log of? 7. Good. Let's try again. Okay. How do I read that, Drew Benton, in orange? Log base 2 of 3. So class, what is the base? And what is the argument? 3. Good. We're taking the log of 3. What kind of log are we taking? We're taking log base 2. All right, good. So as far as reading is concerned, you guys can read these pretty well. All right. So how would I read this up top? I would say this is log base b of a. And we're told that that equals x. All right. Now, I wrote this phrase right here. Can you see it? Can you, the letter C, can you see it? Because if I've got, let's say I've got x equals log base b of a, and I want to convert that into what's called exponential form. Do you guys remember the phrase that pays for radicals? What was the phrase that pays? Power over root, right? So like if I, little time out here. So like if I had, x to the 2/3, and I said, hey, convert that into radical form. You guys would say, oh, Coach Morgan, that's easy. That's just power over root. So x to the second power under the cube root, bada bing, bada boom. You've converted it. Okay. If I want to convert a logarithm, like this equation right here is in log form, and if I wanted to put it in exponential form, the phrase that pays is, can you see it? Can you see it? So in other words, the exponential equation would be b to the power of x equals a. I know that's kooky. I know that seems crazy, but bear with me. If I start with the base down at the bottom and I swoop around to the other side, and then I finish with the argument, that's like a big fat letter C. So can you see it is the phrase that pays. It's how we change from logarithm form into exponential form. Now you might be thinking like, what in the tarnation are you even talking about, Coach Morgan? Well, let me show you. I gave you a little sidebar example with radicals. Let me give you a sidebar example with logs. You remember that? You remember that example that we had earlier where it was 3 to the x equals 27, right? You remember that example? What type of equation is this? Is this a log equation or an exponential equation? It's exponential. Now, again, not to ask a dumb question, but do you see the word log written out? No. So it's not a log equation, so it's an exponential equation. My variable is up top as an exponent. All right. How could I change this into a log equation? I'm going to say, can you see it? Can you see it always starts with the base, and it swoops around, and it finishes back on the same side. This C is backwards because maybe he's looking in a mirror, let's say. But that C still, it starts at the base, swoops around. So this will be log base 3 of 27 equals x. And now we have done something very interesting. We have solved for the exponent. Earlier, we were able to work this one like just using inspection, make the base the same, say, Coach Morgan, x equals 3, right? Well, what if this is something weird like the number 7, and all of a sudden you can't do that anymore? You can still solve for x by using a logarithm. Look what I did there. I didn't really make mention of it while I did it, but I erased the 2. That equation still holds. Now, 3 to what power equals 7? A previously unanswerable question, right? Because we couldn't make the bases the same. I mean, what the dump? 3 and 7, right? But now I've got x solved for. X equals what? Read this left-hand side for me. Log base 3 of 7. Now, thankfully, and I mentioned this earlier, thankfully, we've got a calculator, okay? So the way that my calculator works is I have a LOG button over here. I'm going to hit log of 7 over log of 3, and we'll talk more about calculators on Thursday. But that number right there is about 1.77. So about 1.77 right there. And that's crazy that we could solve for an unknown exponent that's not an integer by using logarithms. Right? Hey, our time is up for today, but check this out. Where we're going to begin next week, or excuse me, next Thursday, is we're going to talk more about this stuff right here, and we might even get to work a couple of examples. Okay? I know this is brand spanking new, and I know you guys are 8th graders, but I think you can handle it. So y'all work hard for me. Live Jesus in our hearts. And no homework tonight. I will see y'all on Thursday. Thank you so much. You guys have